Okay. So, yeah, as I mentioned in chat, I'll be referring to the textbook a lot today because there's a lot of figures and things that are written down in the textbook that are really, really nice to see, and actually a lot of this stuff's kind of impossible to talk about without reference to those figures. But the main thing is I just wanted to save time and not have to have a bunch of stuff copied down, and some of them involve graphs, and I didn't want to reproduce them by hand or anything like that beforehand. So I was just gonna show them in the book. If I was doing this in person, I might have handouts for you all, but instead I'm just gonna show some of these figures from the actual book. So anyway, first thing I wanted to do is, and we're going to be referencing cryptography here and there throughout the rest of the course. But before I get into maybe some of the more complicated crypto stuff, I wanted to give a few examples of some classical cryptography that involves some of this basic number theory that we've been doing up until now. So now that we have taken care of modular arithmetic stuff, we have the basic modular arithmetic stuff we need in order to do this. And so, in fact, you're going to see specifically in our first example of one of the classical crypto systems, you're going to see an example that makes use of this fact of solving linear congruences. So this theorem that we had telling us when we could solve linear congruences is going to be a key thing telling us when it is easy or when it is good to use a particular type of what's called affine encryption. So I'll get to that in a second. But anyway, so I wanted to offer some of these, some examples of these classical crypto systems. As we'll see, they're not these are going to be pretty simple. The high security stuff is more sophisticated and it comes later. So, and we'll talk about that stuff later. But now here's some nice simple applications of the stuff that we've been talking about to cryptography. So before I get into, well, maybe I'll just start out with a specific example. So the notion of a shift cipher, which you've probably heard of before. So shift cipher is like one of the kind of simplest forms of cipher that I can use. So what is, maybe before I talk about this specifically, I can say what is the idea, right? So the idea is I have person A, right, here's person A, and here's person B, okay, and they want to communicate, okay, so they want to send message. So there exists some message that wants to be sent. So we'll say that the message is a single word. Since this example is used in the textbook, we'll say the message is zebra. Okay, that's it. Apparently, if person A says this, person B will presumably understand what it is they mean. The thing is that this is a sensitive word. I don't want anyone to know this message that I'm passing. If I'm person A, I don't want anyone who intercepts this message to be able to read it. And so this message that I'm starting with, the thing that I actually want to pass, is called my plain text. So this is my plain text. This is the actual message that I hope to pass on. Okay. Now, of course, if I just pass person B a note with, or if I attempt to throw them the note from across the room or something, anyone who intercepts it will be able to just, if I just have written zebra on a piece of paper, anyone who intercepts that will be able to read zebra. So my message will be fully readable by anyone who intercepts it, right? Maybe there is a person C. That is person A and B are these are nice people. They're nice and friendly. Person C is angry. Person C is a person of ill repute, and I don't want them possessing my message. So I want to be able to securely send this message, and if person C intercepts my message, the hope is that they won't be able to read it. Okay, only person B will be able to read it. So if I'm sending some sensitive piece of info, it is only readable by the intended recipient. So in order to try to ensure this, I take my message and I scramble it in some way, right? I encrypt it. Okay, so I encrypt this message, and I encrypt it, and I get some scrambled message. I don't know what it is. Whatever this is called the cipher text. Okay. And if this scrambling is secure enough, then I can be secure in saying that whoever intercepts this message is not going to be able to read the cipher text. Okay. So once I have encrypted it, I send it on, right? So I send my cipher text to person B. So person B has cipher text. Okay. And in order to read it, they decrypt the message to turn it back into the plain text, say Zebra. Okay. All right. And so, question. How does the encryption / decryption work? Okay. So again, we're speaking in vague terms right now. So the idea is that the process by which this message, this plain text, is encrypted is going to involve some mathematical thing. Okay, so some mathematical process is involved in encrypting this, and then ideally, in some way, the decryption process is going to be either directly some sort of mathematical inverse or some kind of process that can be reversed. Okay, so the encryption method is going to be reversible in some way that is going to allow my ciphertext to be decrypted, and both of my people A and B are happy. So anyway, the question of how the encryption decryption works, well, that really depends on the method used, right? So answer. There are many methods, so there are tons of options with varying security, with varying levels of security. Okay. Some of these have been used since antiquity to encrypt messages. So one of the first things that we'll talk about, was supposedly used by Caesar, and Augustus also used a different version that was very similar. So there's a lot of options here. But the thing is that the method that is used, the method of encryption, decryption, this requires a key. Okay. So another term that enters here is the notion of an encryption key. Okay. So what does that mean? Well, you might have noticed if I take my text, my plain text, and I encrypt it using whatever method, and I send it from person A to person B. Well, if person B doesn't know how to do the decryption method, right? If they don't know how to decode the cipher text, then they're just as lost as person C that's trying to intercept this, right? So the point is that they clearly have to have some extra knowledge, right? That a random person that might intercept the message is not going to have. That's kind of the point. That extra knowledge is the key. Okay, so the question is, it appears that I'm at an impasse here because I need person A and person B to both possess the key. Right? Person A needs the key because they need the key to encrypt the plain text. Person B needs the key because they need to decrypt the plain text. Okay, and so they both need the key in order for this message to be sent in the planned way. So then, why is that an issue? Well, it's an issue because if this is being done, remotely, right, where they don't have access directly to one another, then how do I get the key from one person to another? Right? So that's a tough question because the idea here is the sending of the key itself, right? You kind of run into a circular problem here where the sending of the key itself is not necessarily secure, right? That in itself would need to be encrypted by some method that uses some other key, and then how does that key get sent between recipients, right? So it's an issue. And of course there are various ways around this that we'll talk about. So you might have heard things like public key cryptography. You may have heard terms like that before. So we're going to talk about various ways that a problem like that would be approached in solving that. So we're not going to worry about that immediately. But anyway, this is kind of the idea here. Is these sorts of general questions are kind of the basic things that you have to ask when you're talking about this process of encrypting a message. So we are going to start with the simplest example of encryption, which is called a shift cipher. So the idea of shift cipher is simply translate each letter value by a fixed amount. Okay, obviously the letter values we're going to talk about, in particular, this depends on the language that you're using. So we are going to be using English, but this process could be done in any language where you have alphabet. So how does this work? So for instance, example. Encrypt Zebra by shifting each letter 4 units to the right. Okay, what do I mean 4 units to the right? I'm thinking of writing my alphabet A to Z from left to right. So shifting 4 units to the right. Here I'm going to have to shift Z. So what do I mean 4 units to the right? I would wrap around, right? And you already probably see where I'm going with this when I'm talking about wrapping around here. So I've run out of space on this sheet. So my first example, going to encrypt Zebra by shifting each letter 4 units to the right. So how does this go? I have the word zebra. I shift it 4 letters to the right, and that becomes Z gets shifted to D, E gets shifted to I, okay, B gets shifted to F, R gets shifted to V, and A gets shifted to E. So I get this nonsense word DIFVE. Okay. Now, due to the nature of how this is encrypted, of course, it's going to send words having a certain, having some length to some nonsense word having the same length. All right, so so it's not masking the length of the word for sure. So anyway, zebra gets sent to this nonsense word. Okay, so then after the ciphertext, so this is the plain text, and this is the ciphertext. So after the ciphertext is sent, it is decrypted, right? By shifting each letter 4 units to the left. So DIFVE gets shifted to zebra. Okay. All right. So one thing that's nice about this process, obviously, is the decryption method is obvious. Once you have specified how you're shifting, then to decrypt, you just shift by the same amount in the opposite direction. Right? So the key in this example, so this was an example, the key is +4. Right? So that's how we can write our key, the plus meaning I'm shifting to the right. Of course, there's nothing special about 4 here. I could have chosen anything there. So I could have chosen shift by 37 units. Okay, but because there's only 26 letters in my alphabet, and because I'm doing this wraparound process, what's actually going on here? Right, so the actual encryption, right, the actual encryption algorithm or encryption method is it takes X, if X is a letter, so we'll say X is a letter, and sends it to X +4 mod 26. Okay, oh, I'm off the... Okay. But what do I mean when I say X is a letter and then I'm adding it and talking about modular arithmetic here? What is it that I'm actually doing here? When I say that X is a letter, it's that for each letter value I've assigned it some X number. Okay, so since the alphabet is 26 letters long, that's where the mod 26 comes in. So for instance, my table would be the following. So note, and there's a warning here beneath this picture that I've chosen A to be the 0th letter. So A is 0, B is 1, C is 2, D is 3, E is 4, and so on, all the way out to Z being 25, right? So note what that means. If I were shifting by 1, right, to the right, then I would take the letter Z, which is 25. I would add 1 to it. I get 26. But mod 26, that's 0, which is A. So this is the wrapping around bit that I mentioned before. Okay. Of course, there's no reason why you have to use 0 through 25 here. You could have used any consecutive integer starting anywhere you wanted to, but of course, just convenient to do so. Okay. So then how do I explain this method? I start out with plain text. I have the key that tells me how the plain text is encrypted to become the ciphertext. So I'm shifting every single letter by 4, which amounts to taking letter, associating to that letter a numerical value 0 to 25, adding 4 to it, and then looking at the result mod 26. This takes care of this wraparound so that Z gets shifted to some other letter of the alphabet, right? So that you don't have to add additional letters to the alphabet. Apparently Augustus did this in his cipher. So if he ended up shifting a letter over, it didn't wrap around. He just added copies of the letter. So apparently modular arithmetic was something unknown to Augustus. Anyway, so this is how this works. And you see that knowing that the key is +4 immediately tells you the decryption method, so you just reverse it. So instead you would subtract, right? You do x minus 4. So the decryption method would just be the opposite thing here, okay? All right, and so that's how it works. So then showing, let's do an example of this fully. So this is the same one the textbook uses. So here's another example. So the plain text is Sparky, we'll say. So in the example in the textbook, they say, suppose that you have used your pet's name, which is Sparky, as your password to your bank account or something. So your plain text is Sparky, and you want to use Shift Cipher, and the key is +1. Okay. All right. So you're shifting every letter by 1. Okay. So what does this look like? So then you're in your picture, or in your process, what it should look like is the following. So your plain text is here. So this is Sparky. So SPARKY. Next is the numerical, so number value of your letter. Okay, so S is the 18th letter. Or P is or I guess S is actually the 19th letter, so it's 18 if we're starting A at 0. So P's numerical value is 15, A is 0, R is 17, K is 10, and Y is 24. Okay, so +1, this is easy enough, so this is just 19, 16, 1, 18, 11, and 25. So then what's the cipher text? Well, so the 19th letter, that's T, or sorry, letter 19, I should say, not the 19th letter. So P becomes Q, A becomes B, R is going to become S, K becomes L, and Y becomes Z. So of course this is a particularly easy shift, but I'm just writing it out to show you exactly how this works. So then what we've done here, of course, is take X and shift it to X + 1 mod 26. Here we had no overflow, right? There was nothing that added up to be greater than, or 26 or greater. So that was it. The general process, of course, that we're using is X gets sent to X + K mod 26, where K is the key. Okay. All right. And so Sparky in plain text becomes TQBSLZ, right? And of course, to decrypt, what would I do? I would just read this backwards, right? So I would start with TQBSLZ, and I would shift to the left 1. That is, I would subtract 1 mod 26. So 19 becomes 18, 16 becomes 15, 1 becomes 0, 18 becomes 17, 11 becomes 10, 25 becomes 24, and I've shifted back to my original word. Okay. So this is a very, very simple way to encrypt messages. It's also a really, really bad one, right? Because of its simplicity, as you might have guessed. So, for instance, right, you can just ask immediately, how many ways are there to encrypt this message using this process? So if you are using a method, right, that is determined by your key, then the number of keys tells you the number of ways that you can encrypt something. So, quick question, how many keys are there in this process? Well, 26, right? There's 26 choices for the value of k mod 26. Those choices are 0 through 25, right? Those are the different things that you can do. So a choice of your key, k being equal to 0, does nothing, right? That's not scrambling the text at all. Okay. Versus a choice of, say, 25, right? That is shifting every letter 25 units to the right, which you might have noticed is the same as shifting it 1 unit, shifting each letter 1 unit to the left. Right. So A gets shifted to Z, B gets shifted to A, C gets shifted to B, and so on. Right. Of course, that's true because -1 is congruent to 25 mod 26. Right. Okay. So that's how that goes. So again, there's only 26 ways in which I could do this. So note, this is extremely easy to break, since there are only 26 keys possible. All right, k equals 0, 1, all the way up to 25. Right, those are the only options. Well, what that means is that since there's only 26 keys, someone who intercepted your ciphertext could just try all 26 of them, right? You just try all of them until you get something that's intelligible, and you assume that that's what it is, that, you know, that's what did it, right? That's the message that was originally encrypted. So the idea is you could just exhaust all the possibilities, right? So when the number of keys is very small, you could just check all of them. So that's why this is bad. So someone who really felt like it could just check all 26 keys to break your encryption. Okay. So one way to remedy this partially, and I say partially because it only increases the amount of keys from like 26 to a little bit over 300, and we'll see why in a second. So one way to remedy this partially is to allow for slightly more complicated transformations. Of course, what I'm saying here, actually, one way to fully remedy this is to allow for vastly more complicated transformations. But the one that I'm going to talk about right now is called the notion of an affine cipher, and it's only slightly more complicated than the shift cipher. So it's a combination of multiplication with a shift. So that's why it's called an affine cipher. If you know anything about terminology coming from geometry, an affine transformation is one that's like ax plus b. Okay, so that is the sort of thing that we're going to talk about. So before I move on, I was going to give you a couple of examples from history. So Caesar apparently used a shift cipher where the key was +3. And Augustus apparently used a shift cipher where where the key was just +1. So Caesar's +3 cipher is a lot of times called the Caesar cipher. So you might have heard of that before. And then Augustus's cipher doesn't have a name, but it's just +1. It's just shifting to the right one. But as I said, apparently modular arithmetic was not something that he considered, and so in the shift, basically whenever you got past the end of the alphabet, so when Z got shifted to being, what would, if a +1 shift would map Z to A under our shift, because we're doing everything mod 26, so 25 + 1, 26, which is 0 mod 26, so that's A. For Augustus, Z became AA. It became AA. So rather than reuse the letter A, a new letter had to be added to the end of the alphabet, which was just a doubling of the letter A. So, which is pretty funny. Anyway, so as I said, this is like the simplest thing. So this slightly more complicated transformation is the notion of an affine. So this is an affine cipher. So how does the affine cipher change? The transformation in question is instead X gets sent to AX plus B mod 26. Okay, so where the GCD of A and 26 is equal to 1. Now, a couple of questions that you might have. So, one, before I wrote this line that I'm requiring the GCD of A and 26 to be 1, you might look at this and say, wow, there's like a lot of possibilities here, right? A lot of possibilities for my key. First of all, how do we label a key? Before, in our earlier process, the key K was just the thing that I added. But here there's two parameters that define this transformation. So the key is denoted by the pair AB. And in general, mathematically, that's a nice way of thinking about this. Key is the key is just a way of organizing all the parameters that affect your process, right? So in this case, this process takes X, shifts it to AX plus B mod 26, and so it is affected by parameters A and B. Now again, before I wrote this line, you might say, oh, this vastly increases, the number of possible keys here, because now I'm counting how many possibilities I have for this pair. But this requirement that the GCD of A and 26 be 1 tells me that the only A that are allowed are the ones that are relatively prime to 26. And so note GCD of A and 26 equals 1 means A is from the list. So A is only allowed to be 1, 3, 5, 7, 9, 11, 15, 17, 19, 21, 23, and 25. Right. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possibilities for A here. Oh, wait. 11. Did I miscount this? 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. Did I miss something? Oh, I didn't write 21 here. Sorry. 21. So there's 12. Yeah, there should be 12 possibilities for A. So 12 possibilities for A. there's 12 possibilities for A, 26 possibilities for B, and since a key is denoted by a pair, I'm counting the number of ordered pairs A, B, where A has 12 possibilities, B has 26 possibilities. So 26 times 12 possibilities for the key, so that's 312 possibilities for my key. Okay, so there's 312 possible keys. That's definitely a good bit more than 26. So this method is naturally going to be slightly more secure. But again, this is a low enough number that, of course, this is very amenable to checking with a computer. It's not so bad at all to exhaust 312 possibilities to break this encryption. So let's actually do this in the same sort of way here. So let's take Sparky and encrypt using an affine cipher with some key. We'll say 3-5. So here, okay, I have my example of let's encrypt Sparky using Affine Cipher with key 3-5, i.e. each letter X, once we've turned the letter into some numerical value, this gets shifted to 3x plus 5 mod 26. Okay. All right. So again, our plain text is Sparky, S-P-A-R-K-Y. Okay. The number value, so numerical value, is the same as before, so it's 18, 15, 0, 17, 10, 24. Okay. And then I want to compute these things 3x plus 5 mod 26. Okay. So 3 times 18 plus 5 mod 26 turns out to be 7. And 3 times 15 plus 5 mod 26 turns out to be 24. 3 times 0 plus 5 mod 26 is just 5. 3 times 17 plus 5 mod 26. 3 times 17 is 51. So 51 plus 5, so it's 56 mod 26 is 4. 30 plus 5 mod 26 is 35 mod 26, which is 9. And then lastly, 3 times 24 plus 5 mod 26 is 25. Okay. And so now, what's our cipher text look like? So now I have to translate this back into letters. So letter 7 is H, letter 24 is Y, letter 5 is F, letter R is 4, or sorry, letter 4. Letter 4 is E, and letter 9 is J, and letter 25 is Z. Okay, so our ciphertext is HYFEJZ. Okay. Okay. So the ciphertext is HYFEJZ. Okay. So how do I decrypt? So how do I decrypt? So before I get into that, I'm going to ask a question, intentionally not answer it, and then go through the question of how I decrypt. Okay. So, in order to do that, I go back to my definition of Affine Cipher, and I look at this, and I noted, right, I computed how many possible keys there were. And something that factored into that, of course, was since this is all mod 26, there was 26 possibilities for B. But because I had this requirement that the GCD of A in 26 is 1, because I wanted A to be relatively prime to 26, this restricted how many possibilities I had for A showing up here. Okay. And so the total number of possible keys using this method was reduced by the fact that I imposed this restriction on A. So naturally then there's a question. The question is, why impose that restriction at all? Why? Right? Why do I require this? Why do I want this requirement? The answer is so that I can decrypt, okay, and have this make sense. Okay, so that's the answer, and we're going to see why I need this. Okay, so let's go back to the example that we did. We took Sparky, we used the key 3-5, and the cipher text we got was HYFEJZ. Okay. So, how do I decrypt then? Well, so suppose I get suppose the cipher text of U is received. Okay, and the key is 3-5. So, me being the person on the receiving end of the message, I know what the key is, and I get a single bit or a single letter, okay, that's been sent to me. The ciphertext I get is just the letter U. So I look at what U is in my numerical code. So U corresponds to 20. And so decrypting U means solving the congruence 3x plus 5 is congruent to 20 mod 26. All right. Where does the 20 come from? 20 is U in its numerical value. Okay, so solving this congruence is what I want to do. Okay. But that's the same as solving the congruence 3x is congruent to 15 mod 26. Now, you can imagine that here, I've used A and B for my key, so I don't want to refer to it as A and B because I've subtracted B here. But in general, of course, I have an expression here. AX is congruent to something, I'll call it C mod 26. So if I wasn't using the specific numbers of 3 and 5 here, this expression would always end up being AX is congruent to some C mod 26. But this is a linear congruence. And I have a theorem that tells me exactly when I can expect a linear congruence to have a solution, okay, or a nice way of solving this. When can I divide here? When can I divide and get a unique solution? Well, it's exactly when the GCD is equal to 1 here, right? It's when they're relatively prime. So I can divide by 3 to get nice congruence, or to get nice solution here, right? So since GCD of 3 and 26 is 1, I can divide by this thing, or by 3, and get that x is congruent to 5 mod 26, so x equals 5 is the solution. I'll give an example of what happens when the GCD is not 1 in a second. But, of course, note that if the GCD is 1, then I can always do this division thing. So to answer the question that I asked previously of why, right, I want to require the GCD to be 1, this is why. Okay, this is the reason. Okay, so what would that mean here? So if x equals 5 is the solution, then what would be the decrypted text? What would be the plain text associated to the ciphertext of U? Thus, F is the original plain text. So I get the ciphertext of U, F is the original. Okay. All right, so let's go back to our example. I have ciphertext HYFEJZ. Okay, so I'm going to copy that. Okay, so let's go back to my example. Ciphertext is HYFEJZ. Affine key is 3.5. So decrypting means what? So decrypting means solving a system of congruences. Okay. So, or I shouldn't say a system of congruences. I get a single congruence for each letter, so I don't have to think. They're not really a system. It's because I'm not solving them simultaneously. They're just a list of 6 separate ones. So, solving 6 congruences. To figure out which congruences I need, I associate each one of these with a number. Of course, this is 7. All right, so this is 7. Y is 24, F is 5, E is 4, J is 9, and Z is 25. Okay, so writing that, the 6 congruences in question are 3x plus 5 is congruent to 7 mod 26, 3x plus 5 is congruent to 24 mod 26. 3x plus 5 is congruent to 5 mod 26. 3x plus 5 is congruent to 4 mod 26. And 3x plus 5 is congruent to 9 mod 26. And 3x plus 5 is congruent to 25 mod 26. Okay. Okay. So those are the 6 congruences that I would solve. Okay. Now I can definitely do it that way, but there's actually a better way of going about this. So, however, there is an easier way to do this. Okay, so the easier way to do this is write Y is congruent to 3x plus 5 mod 26. Okay. Multiply both sides by 9. That means that 9y is congruent to 27x plus 45, which is congruent to x plus 19 mod 26. Okay. Now, why did you do this? Why does this help you at all? Well, 27 is congruent to 1 mod 26, and 45 is congruent to 19 mod 26. Okay, so this is what you get. Okay, why is that nice? Well, this is nice because looking at this, we can rearrange it to say that x is congruent to 9y minus 19. Right, so that's 9y minus 19. Of course, with congruences, if I like, I can always be dealing with pluses here. So this is actually 9y plus 7 mod 26. Okay, and so I've reformulated this decryption process in this way. So what does this mean? I have found the decryption function. And if you track what it is I've actually done here, this is actually very similar to taking ax plus b, right? Say you have a function, you define the function f of x to be ax plus b. You are very well acquainted with how you would actually compute the inverse function of that thing. This is actually what you've done here. You've just done it in the mod 26 world. Okay. All right, so you've done it in the mod 26 world. What is it that you're saying here? Your decryption function. Is 9y plus 7. Okay. So what does this mean? And I kind of ran out of space here. Maybe I should write it here. So note, actually it's a little confusing to write it here. So I write it on a new sheet. So here's an example. Note, multiplication by 9 is the same as division by 3 in the mod 26 world. Right? Okay. And this is true since 9 and 3 are multiplicative inverses. Mod 26. Ah. So in finding this decryption function, what you're actually doing is finding a multiplicative inverse mod 26. Okay. So here is again where the language of congruences helps you out significantly here. Okay. And so what we really did was to turn the function y equals 3x plus 5 into the function x equals 1/3 y minus 5/3. Okay, then converted to integers mod 26. So actually what you did here was what you would have done in Algebra 1. And in Algebra 1, your conversion here is pretty simple. But now you're doing this all mod 26, right? So you're just translating mod 26 here, and you're good to go. Right? Okay, so then the decryption. So the decryption is easy now. All right. So 7, which is the letter H, gets mapped to 9 times 7 plus 7. So mod 26, of course, that's 18. But 18 is the letter S in our table. So then 24, of course, gets mapped to 9 times 24 plus 7. Mod 26. So if you compute that, that is congruent to 15. And 15 is P. And then 5 gets mapped to 9 times 5 plus 7 mod 26, which is congruent to 0 mod 26. So that's A. 4 is mapped to 9 times 4 plus 7 mod 26, which is congruent to 17 mod 26, so that's R. Okay, 9 is mapped to 9 times 9 plus 7 mod 26. So this is congruent to 10, which is the letter K in our correspondence. And then lastly, 25 gets mapped to 9 times 25 plus 7 mod 26, which is congruent to 24, which is Y. And so that gives us our successful decryption here. So Sparky, our original plaintext, is recovered in this way. Okay. Okay. So then, in general, how do I decrypt, right? How do I convert my decryption process into something that I can do generally? So then, in general, to decrypt an affine cipher with my key AB, I have to solve the congruence, y is congruent to ax plus b mod 26. Okay, for x in terms of y. All right, i.e. I solve the congruence ax is congruent to y minus b mod 26. Okay, this is why I need the GCD of A and 26 to be 1. Because otherwise, this solution is not unique. What does that mean? Well, it means that there's ambiguity in the decryption, right? So it means that there is a choice showing up somewhere, which is no good. That is definitely not desirable. So the example given in the textbook is that if you encrypt, I'm making sure that this actually doesn't get blurry. No, it's good. If you want to encrypt using a key of 13 and 5, so if I want to encrypt using a key of 13 and 5 here, so that my encryption function looks like this, so I look at 13x plus 5 mod 26, and I want to encrypt the two words love and hate. So I have plain text love. When I encrypt using this method, I get SFSF. When I encrypt hate, I get SFSF, which, as it notes, that might cause some issues on Valentine's Day, because I get two distinct plain text words. They have the same cipher text, so that's an issue. Okay, so that's the sort of thing that is going to happen when you don't have uniqueness for this decryption function going backwards, right? And you're going to have that issue whenever you have GCD not 1 there. So that's the reason why there's that requirement. Okay. All right. So those are two very simple methods of encryption. They're too simple to be used for anything that matters a lot, just because, as noted, for the shift ciphers, there's only 26 possibilities, so that was really, that could be broken by hand. Theoretically, even the affine cipher could be done by hand. It would just be annoying because there's only 312 possible keys, so the amount of work that would go into breaking in a particular message is not, generally speaking, so much. So those are nice, at least, to see some, this illustrates the key ideas behind encryption in the first place, and the key notion of, an encryption key. No pun intended there. So anyway, so then, there is a general issue with these sorts of encryption. Okay. So one thing that I should mention that is a more general problem than this, as I said, it's not a problem to break the couple of encryption methods we've talked about, but there's a method that defeats them and defeats some other sorts of encryption that you might view as sort of like a meta method of dealing with this. So this is called frequency analysis. Okay. So frequency analysis is the application of some statistical methods to studying the cipher text. Okay, the idea is we can apply a basic statistical analysis of the given cipher text and compare to known statistical properties of the language in question. Okay. So the thing is that, as I said, it's possible to decrypt shift methods without any kind of fancy frequency analysis stuff. There's no need to do that, really, because shift ciphers are easy enough to break anyway. But the reason I want to talk about applying it to shift cipher is that we're going to talk about this notion of frequency analysis later anyway, and so this helps us develop this concept a little bit, since we're going to talk about it later. So what is the idea? So for instance, so this same idea will work in any language, but for instance, in English, E is the most common letter. So E is the most common letter. Of course, naturally, we are making probabilistic or statistics arguments here. So I could construct a sentence that had very strange structure and had a bunch of Z's, right, and not very many E's. I could do that. But in general, if you just take a random sample sentence, E is going to be the most common letter that shows up. Z is the least common. Okay. And so we could just actually look at frequencies of letters in English. So, boom, there we go. Okay. So here is a plot that tells me the rough percentages of the frequencies of letters in a given English text. Okay. So you can just see here that the most common letter is E. E is a little bit over 12%. It's like 12.5%. Okay, so something like 12.5, 12.7% distribution here of E's. So E is about 12.7%. T is like 9-ish%. A is a little bit over 8%, and so on. Okay, and you'll see that Z barely shows up. Q doesn't show up very much. J doesn't show up too much either. Okay, so this frequencies of letters in English. There you go. Right, here's the list. So here is the analysis that's been done on English texts. Okay. Now suppose that we get a cipher text, and this is what it looks like. Okay. So our cipher text is this following string. So there's a bunch of letters. Okay. Now, the idea of frequency analysis is rather than exhaustively checking all of the keys, let's say that I have an idea, I have an inkling that this is a text that has been shift ciphered. Okay, it has had some shift cipher applied to it. Okay, so plain text has been shifted to be this cipher text that I've intercepted. So what I do is I apply this frequency analysis to this cipher text to form a plot. And the plot that I get for that specific cipher text is listed here. Okay, it's listed there. Now you'll note, let's see if I can get it all. Okay, I can kind of, sort of get them on the same plot, but not really. Maybe here. There we go. Okay. So there's our two plots. So the top plot is the frequencies of letters in English in general, and the bottom plot is the frequency of the letters in this cipher text that I've intercepted. Okay. So the idea here is looking at these two. Of course, this is just some small sample of letters, right? This is a relatively small sample of text here. So of course, these frequencies aren't going to match up exactly. Okay, that's expected. Okay, I don't know how many characters here, but there's not that many. So there's 100 characters in the cipher text. So there's only 100 characters here. Obviously, you expect, because the sample size is relatively low, that it's not going to match up. The larger the sample size, of course, the more it would match up somehow. So I look at this, and how does this apply to shift ciphers? Well, I look at this thing and I say to myself, hey, wait, this frequency analysis of the cipher text, this plot, looks like the plot here has been shifted. It looks like it has been shifted roughly 5 units to the right. Okay, and there's a couple of ways you can see that. You could maybe make that guess. But, and again, different samples might yield things that look more or less like this plot. But the thing is, you look at this and you say, okay, these two look similar. It's just that this one has been shifted to the right like 5 units. So I'm saying that this J was an E and this F was like an A. Okay, and so that's what's happened here. Okay, so that this lull here, this Z is my E in this thing. Okay. All right. So then what you do is you test it. You say, all right, looking at this frequency analysis plot, I guess that the cipher text has been shifted to the right 5. So I unshift it. I shift it to the left 5 instead. And when you do that, you get this text. The most commonly used 6-character password is 123456. It is not recommended you use it as yours. So that's, of course, with spaces added here. This is the cipher text that has been decrypted. So that did it. Okay. And again, there's some guesswork there. So that is maybe you look at it and you say it looks like it's been shifted 5, but you try it and you don't get anything intelligible. So then, you say, okay, well, it also looks like it could have been shifted like 9, right? And maybe that works for you. So that is the idea behind frequency analysis and why this might work. Okay, so we'll see that frequency analysis is not something you can do just for shift ciphers, but that's how it would be applied to a shift cipher. Okay, so the idea here of showing you that is that there's a type of cipher that was developed specifically to try to fool frequency analysis. So the idea here is to come up with an encryption method that foils frequency analysis. Now, what would be one way to foil frequency analysis? What would be one way to try to make it a lot less applicable? Well, frequency analysis works because of the uneven distribution of the frequency of letters in English, right? That's why it works. It allows you to match up, right? So I have these big holes here. I have letters that barely occur at all. J, Q, X, and Z barely occur at all in English. So then it allows me to match up the holes here in my cipher text because I just make the argument that, well, there's only a few of these letters that just don't occur, and of course in English it's rare that you have letters that just flat out don't occur. There's only a few letters that are like not used at all. So it's the uneven distribution of the frequency of letters that allows the cipher text or allows frequency analysis to be useful. So what if we came up, and the problem is that shifting doesn't affect that, right? So a shift cipher is not going to change the frequency. So then what if you came up with a method of encryption that in some way was more equitable in its distribution of the frequencies? So the frequencies were spread out and uniformized so that you didn't have these spikes, right, or these holes. And so how would you go about doing this? The idea is to essentially have like a rotating shift cipher. Okay, so it's you have a key that is a rotating shift. So what do we mean by that? So this is the notion of a Visionaire Cipher. So it foils frequency analysis by more equally distributing the letters. So that if we actually looked at the frequency of the letters, it would be more smoothed out. It would be very hard to see how it matched up with the natural frequency of letters in English. Okay, so this leads us to the Visionaire Cipher. Where's the accent? The accent is on it's on the second E. There's 3 E's here. The accent's on the second E. Okay. What's the idea of the Visionaire Cipher? Well, the idea is the following. So another idea here, or listed as an idea. My plain text is this is a secret. Okay. All right. Now I've included spaces here to make this readable as a sentence, but obviously I could not include that at all. I could just write it all in one go. So what is the idea here? The idea is to use a key of some length. So my key is a sequence of shifts. Okay. So my key has some length. You can think of this as like a modern day password, right? So think of this as a password. So let's say my key in this case is going to be encoded as 4 digits. We'll say 2, 4, or 2. What's the exact? So this key cycles. Okay. So this key cycles in the sense that I have a key of length 4. After 4 characters in my plain text, it repeats. Okay, but what do I do with this? So each bit or each number here in the key tells me the shift that I do. Okay, so I shift T by 2 units to the right, so I get V. And I shift H by 5 letters to the right, and I get M. And I shift I by 4 letters to the right, and I also get M. And I shift S by 7 letters to the right, so I get Z. Okay. In this, I shift I by 2 letters to the right instead, so I get K. So note automatically what is going on here compared to our earlier shift cipher. So I have repetitions. I have an I here that is getting shifted 4 places to the right, so it becomes an M in my ciphertext. But here, this copy of I is getting shifted only 2 units to the right, so it becomes a K. So I get shifted to M here, but it gets shifted to K later. Similarly, S gets shifted by 7 units to the right and becomes a Z, but later it gets shifted by 5 units to the right and becomes an X. Okay. Here, A gets shifted by 4 letters to the right and becomes an E. So you see what's in here, right? So what's going on here is different letters get, transformed into, so the same letter potentially will get transformed into a different letter in this shift. So it's more complicated than a shift cipher in this way. Okay, so S gets shifted 7, so it becomes an M. Sorry, not. Is that right? Yeah. That's. Wait a minute. That's not right. If S is getting shifted 7, this isn't an M. S is so S is 18. It's getting shifted 725. This becomes a Z. So this becomes a Z here. E gets shifted 2 to the right. That's a G. C gets shifted 5 to the right, so that's an H. R gets shifted 4 to the right, so that's a V. E gets shifted 7 to the right, that's an L. And T gets shifted 2 to the right, so that's a V. Okay. 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 So my ciphertext is this circled bit. Okay. So to decrypt, is actually just as easy as encrypting, and it's just as easy as encrypting and decrypting with a shift cipher. So to decrypt, my recipient takes the key and shifts in the opposite direction. Okay. So the recipient takes key, shifts in the opposite direction. So here you would take the cipher text. Above or below the cipher text, you'd copy the key, cycling in this way, 2547, 2547, most of it before beginning the chapter 8 bit, where we will start. We'll start back on traditional number theory and leave the cryptography stuff behind for a little bit. So anyway, I will mostly finish chapter 7 basic cryptography stuff on Monday. So anyway, until then, I'll see you all in office hours. I have office hours from 2 to 3:30 today, so I'll post those and I'll make an announcement when I do. Other than that, I will. So I posted homework 3 yesterday. So I will be open to homework 3 questions or any other questions about stuff from the course. So today, office hours 2 to 3:30. I will be there. So normal time.